11.7, the counting principle and permutations. So counting principle, that we did in 11.5, that's the multiplication one. So if a first experiment can be performed in m distinct ways and a second experiment can be performed in n distinct ways, then the two experiments that in that specific order can be performed in m times n distinct ways. So let's use the counting principle. If you want to go ahead and pause the video and write out your letters and your digits that I have below on white, go ahead and do that. Alright, so example 1, counting principles, passwords. A password used to gain access to a computer is to consist of 2 lowercase letters followed by 4 digits. Determine how many different passwords are possible if repetitions of letters and digits is permitted, repetition of letters and digits is not permitted, and the first letter must be a vowel, A-E-I-O-U, and the first digit cannot be 0, and repetitions of letters and digits is not permitted. So that repetition, that means with and without replacement. Let's get that out of the way now. So repetition is permitted. That means with replacement. Repetition of letters is not permitted. That means without replacement. And that's the same thing for C. Repetition is not permitted as well. Alright, so for A, we have with replacement, and B and C, we have without replacement. So let's just keep that in mind as we go through the example. Alrighty, part A. So part A says we need just to create a password with replacement. So our password has to consist of 2 lowercase letters. So it has to be letter, letter, and it has to be lowercase. So I do a lowercase letter. And then it has to be followed by 4 digits. So we have to have 4 digits. So our password has to look like this. This is the template that we have to fill in. We're allowed to pick 2 letters, and then we're allowed to pick 4 digits. And we're allowed to pick any, because it's with replacement. So our password could be AA1111. Maybe I said too much ones, but that's okay. You get what I'm trying to say. So our password can be anything. So if we look, we have 26 letters and 10 digits. So for our first letter, you're allowed to pick any of them, A through Z. Pick any letter you want, so that means there's 26 letters to pick from. Now, since repetition is permitted, aka with replacement, I can pick the same letter again if I want to. So I haven't picked any letters because they're all allowed to be picked again, so I still have 26 to pick from. Now I'm on to the digits. So the digits, it's still with replacement. Repetition is allowed. So our digits, we have 0 through 9. 0 through 9 make up every number that exists in our language and many languages that use our characters. So 0 through 9 create any digit or any number you want. So for our digits, we can pick any number. With replacement, it doesn't matter. So we actually have 10 to choose from. Let's say we pick the number 9. I'm allowed to pick it again. No digits go away because it says repetition is permitted. So I still have 10 to pick from, 10 to pick from, 10 to pick from. So because repetition is permitted, aka with replacement, your picks don't change. We're just talking about 2 groups here, the letter group and the digit group. Because this is not an OR problem, there's nothing to be careful for, we're going to multiply everything. So when we multiply 26 times 26 times 10 times 10 times 10 times 10, we get a really big number. We get 6,760,000. So that means if you set up your password with 2 lowercase letters and 4 digits and you can have repetition allowed, you have 6,760,000 different types of passwords you can create. Okay, let's do B. So B, it's the same setup. We're still doing the same password, 2 lowercase, 4 digits, because that's what we need to do. That's the template for our password. 2 lowercase letters and 4 digits. All right, this time though, it says without replacement. So since it says without replacement, let me change that color. So since it says without replacement, which is repetition is not permitted, we have to be careful with what we're allowed to pick. So first things first, we haven't picked any password yet for part B. No passwords have been selected. No letters for the password. So let's say, now please don't mark up your paper. If you have a tablet, you can do this, but I can erase, so don't mark up your paper when I do this. So let's say for our first letter, we don't have any picked yet. That means we have 26 to pick from. Let's say we chose the letter Z. Let's say that's the first letter we wanted to pick. Because repetition is not allowed, I can't pick that letter ever again. That means there's 25 letters to pick from. Let's do our digits. So our digits, we haven't picked any digits yet. They're all free to pick from. Let's say, so right now we have 10 to choose from. We have 10 because we haven't picked one. Let's say we chose the number 5. Because repetition is not allowed, I can't pick that number 5 again. That means I have 9 numbers to pick from. Let's say I chose the number 4. That means I have 8 numbers to pick from. Let's say I chose the number 3. That means we have 7 numbers to pick from. We're multiplying here. So 26 times 25 times 10 times 9 times 8 times 7, we get 3,276,000 different passwords. So remember, without replacement, one pick to the next, you're always going down in value because you're changing the group of things you can pick from. All right, let's do C. So the same password, we're still setting up the same way. 2 lowercase letters and 4 digits. All right, however though, it says something very specific about what it wants us to pick and not pick. So it says the first letter must be A-E-I-O-U. So that's this one, the first one. So the first one must be A-E-I-O-U. Then it told us that the first digit cannot be 0. And repetition is not permitted. All right, so let's go ahead and just look at our password. Our first one, it doesn't care. It just wants to be A-E-I-O-U. So it wants to have 5. You can only pick 5 here. Because A-E-I-O-U, those are 5 letters to pick from. So let's just say I chose the letter A. Let's say I chose the letter A. So you see how I got rid of it in my alphabet? So the second letter can be anything you want it to be. It can be any letter, but I already chose A for the first one, so I can't choose it again. Let's say we chose, well, it doesn't matter what we choose because we don't have a next letter. So out of all the letters, we have 25 left to pick from. Let's talk about our digits. So our digit can't be 0. So please don't mark up your paper. I'm just going to get rid of it. If it can't be 0, there are 9 digits I can pick from. So let's just say, hypothetically, I chose the number 5. So if I didn't choose the number 5, I have 0, 1, 2, 3, 4, 6, 7, 8, 9. That's 9 numbers left. I have 9 digits left to pick from. Let's say we chose the number 1. Then I have 8 numbers to pick from. Let's say I chose the number 3. That means I have 7 numbers to pick from. So we have 5 times 25 times 9 times 9 times 8 times 7. And we get 567,000 different passwords. It really helps out for these problems that are password specific to write out the alphabet and all the digits and actually like do what we did and cross it out as you go because that'll help figure out how many do I actually have left over. All right, counting principle. At Old Navy, a supply of t-shirts came in. The shirts come in the following color: green, blue, white, yellow, and red. Teddy decides to display one of each color shirt in a row on a shelf. In how many different ways can he arrange the 5 different colors? If he wants to place the blue shirt in the middle, and how many different ways can he arrange the shirts? If Teddy wants the white shirt to be first and the blue shirt to be last, and how many different ways can he arrange them? All right. So A, how many different ways can he display the 5 different color shirts? So we have 5 slots to pick from. Slot 1, 2, 3, 4, 5. It told us 5. And we also have 5 colors. So I have 5 that I can pick from. Let's say I chose green. That means we only have 4 to pick from. Let's say we chose blue. That means we only have 3 to pick from. Let's say I put down a white shirt. That means I only have 2 to pick from. And let's say I put down the yellow shirt. That means I only have 1 left. I know this is without replacement because think about shirts. When you go to a store and you see the different colors, there's not like there's different rows of shirt. If I put a red down, I can't put another red stack down. You know what I mean? That doesn't make sense to put double red stacks down. So we know that this is without replacement because when we put things out, we're not going to put 10 different rows of them. There's going to be 1 row, that's it. Alright, so 5 times 4 times 3 times 2 times 1, we get 120 different ways to arrange these 5 shirts. Where order doesn't matter, we're just throwing the shirts, put them down. Alright, we still have 5 slots to put our shirts down. However, in part B, the blue shirt has to be in the middle. I only have 1 blue shirt in the middle, 1. So, the one in the middle, that's the blue one because Teddy says he wants that blue shirt in the middle. So it must be blue and there is only 1 blue shirt. That means there are 4 shirts. That means we have 4 shirts to pick from. So right now, we have the blue shirt gone and let's say we put the green shirt down. Left over, we could either choose white, yellow, or red. That means we have 3 shirts to pick from. Let's say we chose white. We only have 2 shirts to pick from. Let's say we chose yellow. That means we only have 1 shirt to pick from. Alright, so we have 4 times 3 times 1 times 2 times 1, and we get 24. So if you want the blue shirt in the middle, there's only 24 different ways that you can arrange the colors to the left and to the right of it. Alright, I want you to pause and do C. I know you can do it. Alright, I hope you tried it. So if you were stuck, maybe I'll give you the first hint and then you can pause it. So we're still doing 5 shirts, 5 slots on this shelf. So Teddy wants the white shirt first and the blue shirt last. So put those in their places, pause, keep going, keep trying. Alright, so Teddy is super specific here. The white shirt must be first. There's only 1 white shirt. Alright, we put it down. We can't put it down again because there's only 1 white shirt. Then the blue shirt must be last. There's only 1 blue shirt. We put it down. We can never pick it again. So let's figure out how many left over we have. We have 1, 2, 3 left over. We have green, yellow, red. So we have 3 to pick from. Let's say we put down a green. That means we have two to pick from. Let's say we chose yellow. That means we only have one to pick from. So 1 times 3 times 2 times 1 times 1, we get 6. Permutation. Permutation is an order arranged of a given set of objects. So you might remember this symbol n apostrophe from Algebra 2 if you remember that in high school. So n apostrophe means n minus 1, n minus 2, dot, 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 3, 2, 1. It's a formula, but you're going to see you don't even need the formula. That you're going to know what to do with it when you see it. You'll see what I mean for example 3. Example 3. In how many different ways can 7 different cars be arranged next to one another? So we're going to do this how we've been doing all the other examples where we say we have how many slots to choose from. So we have 7 different cars. That means we have 7 different parking spots. So that means at completely we have 7 cars to choose from. Let's say we parked a car. That means we have 6 cars to choose from. Then 5, 4, 3, 2, 1. Because if you have a collection of cars, you don't have 2 of the same car. Like, you can only have 1 of the same because the VIN number is different and every car is going to be different. Even if you have 2 red Mustangs that are from 1965, one is different than the other. So we only have 7 cars, then 6, then 5, and so on. And we're multiplying this. So 7, 6, 5, 4, 3, 2, 1, we get 5,040. So you see how up here the formula n exclamation point n minus 1 n minus 2 3 2 1. So n that represents in example 3 that represented 7. So 7 minus 1 is 6. 7 minus 2 is 5. Then we go all the way, you keep going until 3 2 1. So because here, it didn't say like put this here, put this here. It just said you have 7 different cars. I don't care how you do it, just put them. That's how I knew we could have just done 7 factorial. 7 factorial is the same exact thing. It's 7 times 6 times 5 times 4 times 3 times 2 times 1. So you start at your number and you multiply down to 1. There is a way to do factorials on your calculator, and I will show you through an announcement on Canvas. So go to your announcements on Canvas and you'll see it there. All right, permutations of 3 out of 5 letters. So let's consider the 5 letters A, B, C, D, E. And how many distinct ways can 3 letters be selected if arranged, and arranged if repetition is not allowed? So you can only pick 1 letter at a time and you can't repeat your letters. All right, we're still going to do this how we've always been doing it. We have 3 letters. And out of all the letters, there's 5 that we can pick from. So we have 5 letters to pick from. Let's say we chose A. That means we have 4 left over. Let's say we chose B. Then we have 3 left over. And we only have 3 slots. So 5 times 4 times 3, we get 60. Now, the difference between example 3 and example 3, it's not saying you have this many, choose this many. It's just saying you have 7 cars, throw them in their parking spots. Nothing specific. In example 4, it actually got specific. It says, I only want 3 out of the 5 letters, and repetition is not permitted. You're going to see how example 3 and 4 actually set up our permutation formula. So combining example 3 and 4 actually help us find permutations, which is example 5. So permutation formula, the number of permutations possible when our objects are selected from n objects is found by the permutation formula. NPR equals n factorial over n minus r factorial. Now this looks super complicated. That looks like a very intense formula, but you're going to see when we break it down, it's actually not too bad. So let's bring out things. So our R, that's how many we're picking. and your n is your total. So your r is how many you're picking, and your n is your total. So just like in example 4, if we said I have 5 letters but pick 3, your n would be 5, and you're picking 3. You could actually use the formula and you'll still get 60. Alright, let's actually use that formula in a new example. You are among 9 people forming an astronomy club. Collectively, you decide to put each person's name in a hat to randomly select a president, a vice president, and a secretary. And how many different arrangements or permutations of officers are possible? So, order matters here because if I get chosen as president, I can't be vice president, I can't be secretary. So once someone gets picked, they're picked and no longer can be picked again. Because let's say you get picked for secretary. That means you can't be vice president and you can't be president. So you can't be picked again. So order matters here because if we pick someone, they affect the rest of the group. That's how I know that this is a permutation. It also asks for how many different arrangements are permutations, but I know that this is a permutation because order matters. I'm going to send out also an announcement on how to really decipher between permutation and then when you get to it 11.8 combination. So because this is a permutation, I know I'm going to use my formula NPR equals n factorial n minus r factorial. So we need to identify two things, our n and our r. So your n is your total. That means in this example, everyone in the club. There's 9 people. Your r, that's how many you're selecting. So you're selecting a president, a vice president, and a secretary. So you're selecting 3 out of the 9 people. So let's plug it into our formula. Remember, if we're using a formula, it's a template. So let's fill out the template. We have blank factorial over blank minus blank factorial. So we have n, which stands for 9, and then we have r, which stands for 3. Now, go to your announcements and look up how to do this with your calculator if you have one. It's so easy. But I'm going to show you also how to do this by hand. So let's simplify our parentheses. So we technically have 9 factorial over 6 factorial because 9 minus 3 is 6. This part right here is only important if you're using a calculator. If you're using a TI-84. So if you're doing this by hand, ignore the boxed part. You just need what's on the right of it. So 9 factorial, that stands for 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. Now, because there's no plus or minus in here, you can cancel out numbers that are identical. So 6 is identical, 5, 4, 3, 2, and 1. So what we're left with is actually just 9 times 8 times 7, which is 504. Permutations of duplicate objects. The number of distinct permutations of n objects where n sub 1 of the objects are identical, n sub 2 of the objects are identical, dot dot dot, n sub r of the objects are identical is found by the formula n factorial over n sub 1 factorial, n sub 2 factorial, dot dot dot, n sub r factorial. Again, another formula that seems way scarier than it actually is. Let's break it down. So the top part, that's actually saying your total factorial. Your bottom part, that means you're repeating characters. And you're going to have multiple of them. You could have none of them, you could have multiple of them. So, in how many different ways can the letters of the word Cincinnati be arranged? So first thing, let's find our total, meaning how many letters do we have? We have 10 letters. So our n is 10 because we have 10 letters in the word Cincinnati. Now, let's look for repeating characters. So repeating, we have 3 I's. We have 2 C's. And we have one more repeating character. We actually have 3 N's. So those are our repeating characters. All right, let's set up this formula. You're going to see what we're going to do with them. So on top, we have our total factorial, so that's 10 factorial. And on the bottom, we put our repeating characters, meaning we have 3 factorial, we have 2 factorial, and we have 3 factorial. And now we just do it how we just did our permutations. So 10 factorial, that's 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. You're really going to want a calculator for this. And then we have 3 factorial, so that's 3 times 2 times 1. 2 factorial, so 2 times 1. And then another 3 factorial, so 3 times 2 times 1. Let's go ahead and cancel some stuff out that looks identical. So 3, 2, 1. If you see it, you can actually cancel out 6. 3 times 2 is 6, so you can do this. If you want to, you can do that. I'm not going to do that for this example because a lot of us aren't going to see that, but if you see it, you are allowed to do that. That's totally okay to use. Alright, so on top we have 10 times 9 times 8 times 7 times 6 times 5 times 4, and when you multiply all that together, you get 604,800. 3 times 2 times 1 times 2 times 1, we get 12. 604,800 divided by 12, we get 5,040. Or sorry, 5,400.